All right, let's talk about something we get wrong pretty much every day: the difference between mass and weight. Yeah, I know, we use the words like they're the same thing, but in the world of physics, they are worlds apart. Let's get into it. Okay, let's jump right in with a scenario. You go to the doctor, they put you on a scale, and your chart says you weigh 70 kilograms. Sounds perfectly normal, right? We all say it. But what if I told you that statement is, technically speaking, completely wrong? You see, this is where the whole mix-up starts. In our everyday lives, saying, I weigh 70 kilos is totally fine. No one's going to call the physics police. But if you're an engineer trying to land a rover on Mars, or a scientist calculating the orbit of a satellite, getting this wrong isn't just a simple mistake. It could be a catastrophic failure. The distinction is absolutely crucial. So, to clear this all up, let's start with the first piece of the puzzle: mass. The easiest way to think about mass is, well, it's all the stuff that's packed inside of you. The key word here is intrinsic. Your mass is a fundamental part of you. It's the total amount of matter, all the atoms and molecules that make you, you. And here's the important part: that amount of stuff never, ever changes, no matter where you go. Whether you're on Earth, on the moon, or floating in deep space, your mass stays exactly the same. It's constant. Okay, so if that's mass, then what's the deal with weight? Well, if mass is the stuff inside an object, you can think of weight as the pull on that stuff. And this right here is the absolute game changer. Weight is a force. It's the force of gravity yanking on an object's mass. And because the force of gravity is different all over the universe, your weight is not constant. It can, and absolutely does, change depending on your location. So let's just put them side by side to really nail this down. Mass is a measure of matter. It's constant everywhere, and we measure it in kilograms. Weight, on the other hand, is a measure of force. It changes with location, and its proper scientific unit is the Newton. So that 70-kilogram reading from your doctor, that's actually your mass, not your weight. So how are these two things actually connected? Well, it all comes down to the super simple but powerful little equation. Your weight equals your mass times the acceleration of gravity, which scientists just call g. This formula is the bridge between the two ideas. So what's that g all about? Well, here on the surface of our planet, the pull of Earth's gravity is about 9.8 meters per second squared. So if you take an object with a mass of exactly 1 kilogram and use that formula, you find out its weight on Earth is 9.80 newtons. That's the actual force pulling it toward the ground. Okay, this is where the light bulb really goes on. To see this difference in a big way, we gotta get off this rock. Let's take a quick trip to the moon. Now check this out. Let's say we have an object, and its mass is 5.0 kilograms. On Earth, with its strong gravity, that object weighs 49 newtons. But now take that exact same object to the moon, where gravity is way, way weaker, and look what happens. The mass is still 5.0 kilograms. Remember, the amount of stuff hasn't changed, but its weight just plummets to only 8.4 newtons. See? Same mass, totally different weight. It's proof. This brings us to another huge misconception, something we see all the time in those incredible videos of astronauts floating around on the International Space Station. We call it being weightless. But is that what's really happening up there? So let's ask the big question. Based on everything we just learned, that weight is the force of gravity pulling on you, are those astronauts truly weightless? Does gravity just switch off a couple hundred miles up? And the answer, you might be surprised to hear, is a huge nope. Not even close. The space station is actually so close to Earth, relatively speaking, the gravity up there is still about 90% as strong as it is down here on the surface. So an astronaut still has almost all of their weight. They are definitely not weightless. So if they're not weightless, what in the world is going on? The correct term is free fall. The space station, the astronauts, and everything inside are all constantly falling towards Earth. But they're also moving sideways so incredibly fast that they keep missing it. That feeling of floating is really the sensation of endlessly falling, without any floor or chair pushing back up on you. You know, there's a really fascinating little detail here. The source material points out that even when we drop something here on Earth, it's actually never in a state of perfect free fall. And why is that? It's because of air resistance. As soon as something starts falling through our atmosphere, the air itself starts pushing back up on it. True, perfect freefall can only happen when gravity is the only force acting on you, which is exactly what it's like in the vacuum of space. Okay, Let's bring it all home. If you only remember one thing from all this, make it this simple idea. Mass is the stuff, weight is the pull on that stuff. One is a property of you that never changes, and the other is a force that depends entirely on where you are.
And that leaves us with a final thought experiment for you. We've talked about the moon, but what about Mars? If you were standing on the red planet, knowing your mass would be exactly the same as it is here, but the pull of gravity is only about a third as strong, what would your weight be? Something to chew on. Thanks for tuning in.